Hello, everyone. Today I'm going to talk about ignition and the propagation of laminar spray flames. The work here is mainly done by the research fellow, Dr. Li Qiang and Dr. Li Shangpeng. So I will first introduce the background of our work. So liquid fuel actually has many advantages, and it is injected into the combustion chamber and breaks into the droplets to generate a spray. Okay, and then these sprays typically evaporation and combustion as a group. So it is a very complicated process, and including the primary breakup and secondary breakup, and then we will have the vaporization. The fuel vapor and air, they will have the mixing, and finally the combustion process downstream. We already have different researches about like the experiments and the numerical simulations for spray frames. Normally we focus the ignition of the spray frames and also propagation of the spray frame. So for the ignition, typically the important parameter is the minimal ignition energy. Okay, it is affected by different liquid fuel properties. This has been studied by many different researchers, like the Lefebvre. They focused on the minimal ignition energy as a function of the pre-vaporization degree. Okay, and also the minimal ignition energy as a function of the droplet diameter. So recently, because we have advanced measurement techniques, so we can further visualize the flame dynamics, such as the work done by the Oliveira from University of Cambridge. So here we can see the long mode and the short mode. For the propagation of the spray frame, we also interested in how the liquid fuel droplet properties affects the propagation speed. Okay, such as the liquid equivalence ratio. Okay, and also different droplet diameters. And for flame dynamics, actually, when the spray frame is initiated from a spark or from a laser, it propagates outwardly, and we can observe the peculiar flame dynamics, such as the flame oscillation. You can see there's actually the periodic changes of the flame speed. And also we can observe the cellularization of the flame front. Okay. All these actually behaviors are affected by the interaction between the flame and the droplets. So here I present some very interesting results measured from different experiments, such as this one. So we can see, there is an interaction between the flame and the droplets. The flame front may be wrinkled, and the droplets, may evaporate and burn in the post flame zone. Okay. And in all these cases, actually, we can see there is a clear-cut interface between the combustion product and the two-phase mixture. Okay. However, although we have different, we already have lots of the studies about the laminar flame spray. However, how the flame and the droplet actually they interact with each other, this is still not well understood. So in this book, we will conduct the theoretical and also the numerical simulation to reveal their interaction. Okay, so so this actually is a physical problem. This is a fuel mist, and then we ignite at the spark. Okay, put a sufficient energy. If the energy is large enough, then we will have the successfully initiate the flame front. Okay, so for spray frame, because the droplets will be interacting with the flame, so we will have two different scenarios. For the first scenario, if the droplet is large and if the evaporation rate is slow, then we probably also have the droplets behind the flame front. Okay, and another scenario is that if the droplet is very small and if the evaporation rate is high, so when the droplet across the flame front, it will get fully vaporized. Then behind the flame front, we will not have any droplets. Okay, so how to characterize the problem? So here we introduce two fronts. The first is the evaporation compression front. Okay, so this is the location where the droplets are critically vaporized, and this is an interface between the two-phase mixture and the gases mixture. And another one is the evaporation onset front. Okay, so this is normally on off the flame front, and this is the location where the droplets start to vaporize. Okay, so based on the location between the evaporation compression front and the flame front, so we can further define the homogeneous and the heterogeneous flame. So if RF is less than RC, and at the flame front, the mixture is gases, and we call it a homogeneous flame. And if RF is larger than RC, we will have the two-phase mixture at the flame front, and then this is the heterogeneous flame. Okay. So this is a mathematical model, and we consider 1D configuration, and it is a quasi-steady moving flame front, and the thermal properties are constant, such as density, conductivity, and also the heat capacity. And we assume the activation energy is sufficiently large, and for the liquid phase, it has reached the kinematic equilibrium, okay, with the gas phase. And then we consider mono-dispersed dilute filled sprays. Okay, so these are the governing equations for the model. Okay, the energy equation and the species equation, and the last one is the droplet mass loading equation. Okay, so here I present the chemical reaction model and evaporation model and the boundary conditions. So for the evaporation model, here it is a function of omega. Omega is the heat exchange coefficient and also the droplet temperature. Okay, and QV here, it is a normalized latent heat. Okay, so for the boundary conditions, for when eta equals minus RF at the spherical center, so we put the numerical spark here. Okay, and then zero gradient for the species, and for the droplet loading, it is 0. And for another boundary, eta is plus infinity. So we have the droplet there with the loading of delta. Okay. So and then we to solve the governing equations with the proper boundary conditions we mentioned just now, we will have the correlations for the spherical flame, the correlation for spherical flame ignition and propagation. Okay, so the details can be found in this paper, as you can see here, and this actually involves the flame speed, flame temperature, evaporation onset front, and evaporation compression front. Okay, and this correlation also involves different gas and liquid properties, such as the Lewis number and the droplet mass loading and the latent heat of vaporization. Okay, so the novelty of this model is we can reveal the evolutions of flame front and the droplet evaporation front. And we can also describe the transition between the homogeneous and heterogeneous flame. So here I show you some results, the trajectory of flame front and the evaporation zone. So first look at the right figure, and it is U as a flame propagation speed as a function of the RF, so with different ignition energies. So when we increase the ignition energy, the flame kernel branch and the flame propagating branch, they move towards each other. Okay, so if the energy is higher than the minimal ignition energy, then the flame can propagate successfully from kernel state to the spherical flame. Okay, so for this different flame branch, we can see actually we can further look at the evaporation compression location at C here. Okay, for the flame kernel, we can observe the transition from heterogeneous to homogeneous. Note that FF here actually it is a flame front. Okay, eta equals 0. Okay, however, because here it is a flame kernel branch, and the Q is less than the minimal ignition energy, so the flame actually stops at the flame ball solution. Okay, So for higher ignition energy like this one, we can observe the successfully propagate of the flame. And at C, the first, is negative. It is a heterogeneous flame, and then transit into a homogeneous flame, increases, and finally, reach a constant value here. Okay. So for delta eta, it is the radial thickness, okay, of the evaporation zone. So this is a difference of eta V and eta C. We can see, it changes non-monotonically during the flame propagation process. Okay. Just now we talk about the results with the unity Lewis number. So here we first look at the Lewis number effects. So we consider Lewis number equals 0.8 and Lewis number equals 0.2. Okay. So for we further consider 4 cases with different values of omega and delta. So for when Lewis number is less than 1, let's say it is 0.8, so HM and HT flame transition occurs earlier. Okay. And multiple transition between the HT and the HM states observed, when the omega it is small. Okay. Normally, delta eta, the thickness of the zone, evaporation zone, generally increases with droplet loading and decreases with the heat exchange coefficient omega. For large Lewis number, like here, and the flame generally propagates in the gaseous environment. Okay, so it is a homogeneous flame. For spray flame propagation, we can see actually flame bifurcation occurs when we have intermediate omega. Okay, so if we further increase the heat exchange coefficient omega, we can only have the weak flame. Okay, so normal flame and a weak flame actually they have the different flame propagation speed. When it is moved outward. And then for the evaporation completion front at C, okay, for the weak flame, it is very close to 0. That means actually it is very close to the flame front. And for the normal flame, it is negative, like this one, and this curve. Okay, so it is way behind the flame front, and it is a homogeneous flame. So the capacity of the model to predict the transition between the homogeneous and the heterogeneous flame can be further confirmed if we look at the flame structure, okay, around this curve. So here we take three cases, E, F, and G. Okay, so for E, actually, YD has finite values at R equals 0. However, F, it is at 0. And then for G, it is already 0. And the evaporation completion front move off the spherical center. Okay. And then we further look at the Lewis number effects for the flame propagation speed. And the flame propagation speed U increases with delta because of the spray enrichment effects. Okay, as you can see from this group, the gaseous flame, and the 2 spray flames. Okay. Also, the U decreases with the Lewis number when the flame radius is small or intermediate due to the flame stretch effects. Okay. For heterogeneous flame, the speed at a large flame radius changes with different Lewis numbers. Normally, Markstein length, it is used to measure the effects of the stretch on the flame propagation speed. Okay, so U equals U0 minus L, and by K is the stretch rate, and U0 is the laminar propagation speed without stretch. Okay, so we can see we can observe the enhancement or reduction of the flame speed. Actually, they are weakened due to the droplet addition. Okay, so this is the gaseous flame, and when we load the droplet, so the magnitude of L actually it is reduced. Okay, and also we can see Markstein length shows weak dependence on omega. So here we change omega from 0.1, 0.2, and 0.4. Basically, limited influences can be observed. Okay, so these are the numerical results, and normally, these are theoretical results. Normally, if we would like to further look at the details and the physics behind the spray frame, ignition, and propagation, we need to do the detailed numerical simulations. Okay. So the problem schematic actually it is similar to the theoretical analysis. So these are the droplets, and we put the spark here, and we may initiate a flame if the ignition energy is large enough. Okay. So what are the initial conditions? So here we consider two-phase mixtures, air and the ethanol droplets. So the droplet equivalence ratio is 0.4 to 6. And here, these are the monodispersed dilute sprays. Okay, so we have a uniform distribution. So the initial pressure and the temperature, it is 1 atmosphere and 298 Kelvin. So the initial droplet diameter, D0, we consider in this work is 5 to 15 micrometer. We use ASIF, the in-house code ASIF, to simulate the two-phase flow simulation. And we consider the adaptive mesh refinement, and the finest mesh size here, it is 16 micrometer. And the detailed chemical mechanism is used for ethanol combustion, and the ignition at the speckle center here, it is modeled using this form. So this actually, it is a function of time and also the radius. Okay, so here we use the Eulerian-Eulerian method to model the spray frame. Okay, so these are governing equations, and for the gas phase. Okay, so at the right hand side of the governing equation, we have the SL and S2. So SL are the two-phase coupling terms. Okay, I list the details here for the mass, for the momentum, and also for the energy. For the ignition, SI is the ignition model. So the expression, as I already mentioned, in the last slides. Okay, so these are the governing equations for the liquid phase. We solve the equations for the droplet diameter, the velocity, temperature, and the droplet number density. Okay, and this solve actually has been validated and verified with different cases, like for the mass and energy exchange models, and the momentum exchange models, and the evaporation models, and so on. Okay, so here I'm first going to talk about 3 cases. They are with different liquid equivalence ratios. So with a relatively low case, 1.75, and a relatively high case, 3.0. Okay, they also have different, 2 droplet size. One is 5 micrometer, and here it is 15 micrometer. Okay, so they have because here we don't here in the gas phase it is only air, so the gas equivalence ratio is 0. And for all these cases, the ignition energy is 6 millijoule. Okay, so we consider 3 cases, and we show the fuel vapor mass fraction and the gas temperature and the gas velocity for these 3 cases. Okay, as you can see here, the flame kernel is always born in sprays but grows in gaseous mixture. Okay, so for case 1, we can observe 3 stages from 0 to A, and then A to B, and B to 3. So from A to B, actually, the flame has very limited propagation. So flame radius here, actually, it is almost constant. Okay, however, the evaporation completion front moves outwardly continuously. Okay, for case B, we only have the normal, normal flame propagation, and the distance between the flame front and the evaporation completion front, it is small. And for the last case, we can see different phenomena. Okay, first, from O to C, we have the ignition, and then C to D, the RF, the flame front actually, shrinks. So it signifies extinction. And then for the last stage, D to E, and E beyond, actually, we have the reignition phenomenon. Okay. So in order to further understand actually different, dynamics behind these three cases, we choose delta R. Delta R actually it is the distance between RC and the flame front, and the evaporation compression front and the flame front. Okay, and we also calculate the equivalence ratio at the flame front. Okay, so this actually based on the element like carbon, hydrogen, and oxygen. Okay, so for case A, we can see initially it is delta R is less than 0, so it is a heterogeneous flame. Okay, and then we can observe, there is a 0 crossing point. Okay, so here delta R equals 0. Delta R equals 0 means now RC equals RF. Okay, so this actually indicates a transition from the heterogeneous flame to homogeneous flame. A and B, as I mentioned just now, it is quasi stationary frame. Okay, so during this period, actually, delta R increases significantly. Okay, because the evaporation compression front, propagates outwardly continuously. Okay. So here, UFL and LFL, they are the lower and up permeability limits of SNL field. Okay. So during whole this period, actually, it is in between. Okay. And when the flame propagates steadily, the equivalence ratio here it is around 0.65. It is 30% of the liquid, the initial liquid equivalence ratio. Okay. Then for this case, actually, the whole process it is delta R, it is relatively constant. Okay, and then for the 5 EFF, okay, the equivalence ratio at the flame front, it is first increase and reach a peak here, and then decreases very quickly. The last one, it is more interesting. The last case, we also observe the transition between the heterogeneous and homogeneous flame. Okay, so from C0 to C, actually, C, the sparking period, the equivalence ratio increases very quickly. And once the spark is off, the equivalence ratio decreases to around like 0.8. Okay, it is still about 1. Okay, it is still about 1. And then gradually decreases. Okay, finally, it is around 1.38. Okay. Then we analyze the time scales. Okay, so the reaction time scale, mass diffusion time scale, thermal diffusion time scale, and the last one is the evaporation time scale. So for case 2, heat and few species diffusion time scale between two fronts, they are very close. Okay, and then for case A, near point A, okay, A actually is just that are indicated in the last slide. Okay, so near A, the mass diffusion time scale is higher than the reaction time scale, and the thermal diffusion time scale it is larger than the evaporation time scale. So the fuel vapor and the thermal diffusion is too slow to maintain a propagating flame. Okay, and after B, okay, you look at here, and the tau M and tau T show a slightly earlier reduction. So that means actually the mass and thermal diffusion play an important role to reinitiate the flame. Okay. For case 3, after C, okay, after the instant here, tau R, the reaction time scale gradually increases. So both tau M, tau, and tau T increase and peak at the D due to the largest diffusion length. So the flame is reignited after D, and then all the time scales decrease. Okay. For minimal ignition energy, we can look at this. So here we show the dependence on EMIM or MIE as a function of the liquid ER. So we can observe the U shape. So this is the left branch, this is the middle branch, and this is the right branch. Okay. So for the right branch, for the left branch, we can observe the quasi-stationary flame kernel as we introduced just now, case 1. And for the right branch, we will have very high liquid ER, and then the evaporation heat loss is high. Okay, so for the middle branch, actually the minimal ignition energy has a very weak dependence on the liquid ER. Okay, actually we also discuss, we also investigate the dependence of MIE on the equilibrium ratio when we have the pre-vaporized vapor, okay, few species in the mixture. So for some of the cases, we can observe the similar U-shape, okay, and for some of them actually not. So the detailed discussion actually, can be found our recent publication in Combustion Flame, okay. So there we correlate actually, the spark ignited kernel dynamics and the minimal ignition energy. So another interesting phenomenon we observe from our simulation is the ignition failure. Okay, so as I mentioned just now, the Oliver actually revealed the long mode and short mode based on the measurements. So here I show the images from their paper. Okay, so in our simulation results, we can also observe the long mode and short mode. So the long mode actually it is at when we have relatively low equilibrium ratio. However, for the short one, we normally we may have high equilibrium ratio. Okay, so they have different actually behaviors. For the long ignition failure mode, the flame ER is close to the lower flammability limit. Okay, and normally the OH concentration is high, as you can see from here. However, for the short ignition failure, the flame ER is way above the up flammability limit, and the OH concentration is low. Okay, so this actually, we can see a good agreement between the experimental observation and also the numerical results. For this part, we also would like to discuss about the oscillating flame propagation. So here we show two cases, phi L equals 3.0 and phi L equals 2.5. Okay, so for both of them, we can observe the oscillation, but the frequency is different. Okay, and flame oscillation occurs, when the initial droplet diameter is higher than 10 micrometer, and the oscillating propagation always happens in homogeneous flame. And if we zoom in one period and we look at this figure, okay, it is from 10 centimeter to 14 centimeter. Okay, we can see actually, the flame ER and the flame distance, they have some phase difference. Okay, the oscillation frequency increases with the liquid ER. This can be this is also seen, from the frame this figure. Okay, so here we show three diameters: 10 micrometer, 12.5, and 15 micrometer. For all of them, actually, we can see F, the oscillation frequency, exhibits linear correlation with the liquid ER, and the oscillation frequency decreases with droplet size for fixed liquid equilibrium ratio. Okay. Okay, so we still have some time. So here I would like to introduce our recent work about single droplet evaporation and autoignition. So these two, this part of work has been published in our recent in Combustion Flame and International Journal of Heat and Matter Transfer. Okay. So this is the schematic of the problem we would like to study here. Okay, so because as you know, actually, classical quasi-steady model have some limitation, and there we assume actually the processes at the gas phase that it is much faster. Okay, the time scale actually there is much shorter than the Z of regression of the droplet surface. Okay. So if we have, if we consider the problems on the elevated pressure, then the quasi-steady assumption may be invalid. Okay, so here we consider single component full droplet, and it is quiescent, and in the quiescent, oxidizing, and hot environment. Okay, so here we don't consider gravity, and there is no radiation, and so this is the governing equations for the for the droplet evaporation and also the ignition. Okay, so this is the continuity species and also the energy equation. Okay, and for the initial conditions, we have this is the initial conditions, and then for the boundary conditions at the droplet phase. Okay, you can see from here, and we only consider the one-step reaction. So few react with O and have the product. So this is the reaction rate. Okay. Okay, so the classical actually, quality steady model normally assume, the gas phase convection and diffusion much faster than the droplet surface regression. Okay, so this actually normally, deviates from the real scenarios. There, the density ratio of the liquid to the gas phase, normally it is high. Okay, so we need to introduce actually the concept, or we introduce the concept of the evaporating boundary layer to consider the gas transient effect. Okay, and so this is the equation, okay, for the droplet diameter, droplet radius here, and if we numerically integrate this equation, we can have the results here. So this actually is a droplet size as a function of the normalized time. Okay, so here Q as dE, this is from the quasi-steady theory. Okay, so K, as you can see, it is related to the liquid droplet density ratio gamma, and also the spotting number BV. Okay, and normally, small kappa, okay, indicates a significant gas transient effect. Okay, so as we can see from here, when kappa equals 1, 2, 3, and 10, and 100, when it is 1, it has a very large error to the classical QS model. Okay, so when actually kappa is high, let's say it is 100, it is very close to the classical results. Okay, so that means actually, if we would like to consider the situations with reduced density ratio, we must consider the gas transient effect for droplet evaporation. Okay, and then for droplet autoignition, we can have this asymptotic thermal equation in the ignition zone, and the ignition actually, can be the ignition criteria with the gas transient effect can be derived as here. Okay, so delta, so I here, it is the Damcolor number. Okay, instantaneous Damcolor number of the system, and delta C is the time average Damcolor number during the droplet evaporation. Okay, so this actually, it is a Damcolor number as a function of Rn. Rn is the droplet size. Okay, so as you can see from here, the ignition can be reached at this critical point for different cases. Okay, so we further compare our theoretical results with the transient simulation. Okay, so basically, actually, we can find our theoretical results can be have a good agreement with the transient simulations. Okay, and this is actually, we further compare the critical droplet ignition temperature, okay, as a function of the RD0. So for both cases, actually, the ignition temperature increases monotonically as RD0 decreases. Okay, and the quality steady results somehow, underestimates the ignition temperature, particularly, when we consider the small gamma and RD0. So our results actually agree very well with the transient numerical results for different conditions. Okay, so from the right one, we can see our theory can agree well for different YO infinity. Okay, and if we increase the YO infinity, it promotes ignition and reduces the ignition temperature. So when the YO infinity is not very small, okay, not too small, so it is actually generally not a limiting factor for ignition. Okay, so these are the comparisons between the simulation results and the theoretical results for the single droplet ignition and evaporation. Okay, so these are the conclusions. So we developed a theoretical model to study the ignition and the propagation of laminar spray frames, as well as the evolutions. This model can also predict the evolutions of the droplet evaporation zone. So we introduced the concept of evaporation onset and the completion fronts, okay, to quantify the movement of the evaporation zone. So the transition between homogeneous and heterogeneous frames can be captured. The radial thickness of the droplet evaporation zone changes when the flame propagates outwardly. The Lewis number significantly affects the evolutions of the droplet evaporation zone. From the detailed numerical simulation, we observe different spray frame behaviors, such as a quasi-stationary frame and thermal extinction and reignition. And the dependence of the MIE with the liquid equilibrium ratio is discussed, and its correlation with the frame dynamics are identified. So the mechanisms of long and short ignition failure mode are discussed as well. Oscillating flame propagation in fused frames is observed, and we discuss the underlying mechanism through visualize the flame ER and the flame distance. Then for the last part, we briefly introduce the single droplet ignition and evaporation and ignition. So here, the gas phase transient effect is studied through considering the evaporating boundary layer. It is found to be important for smaller liquid gas density ratio and higher evaporation intensity. Okay, so this work is supported by NUS and the MOE of Singapore, and the simulations are run in National Supercomputing Center. Thank you very much.